Okay, so one of the first things I'd like to talk about are types of functions. So what we're embarking on now is our journey to get shortcut derivative rules. And the rules only work for certain types of functions. And so if you can't figure out what type of function you have, then you might be applying the wrong rule. So this is an important thing to pay attention to. So if you don't know the shortcut, then you can always use the definition. So the side thing is, until we cover the type of function in the shortcut, we have to use the definition. We won't be able to do anything other than that. Okay, but if we have a powered function, power functions look like x raised to some power, okay? Then the derivative of x to the power is going to be, you multiply that power out front, write down your x, and then your new exponent is 1 smaller. So there's a request in the chat window. If you have something like 32x to the p plus 2, the derivative of that, well, first of all, we haven't really talked much about this, but the 32 just kind of tracks along. One way you could think about this is derivative is giving you slope. So if you think about a slope of a function, if your function gets twice as tall, is the slope also going to get twice as steep? So if your function's slope increases, if the function y values increase, the slope should also increase. So it should make sense to you that if my function has a multiplier in front of it, that multiplier needs to be part of the derivative as well. Okay, and then you would just multiply by that exponent. And then you would subtract 1 from the exponent. So p plus 2 minus 1 would be p plus 1. So that'd be an example of handling that one. It's just kind of working on it in general, okay? So the power rule is the rule to use on power functions. And what you need to recognize is a power function is the variable is in the base and the power is in the exponent. One misconception that shows up a lot is when we move on to exponential functions. How can we tell the difference between an exponential function and a power function? Let me know in the chat window. So in an exponential function, we're going to swap the role of the variable and base like power functions. So it's actually going to be some number raised to the x. So the variable is now in the exponent, right? Exponent. X is in the exponent. That's an exponential function. Variable is in the exponent. So examples would be 2 to the x, 3 to the x, e to the x, negative 10 to the x. I don't know. Something along those lines. Okay, so if we have a to the x is a generalized exponential function, the derivative of a to the x, let me know if you know this one in the chat window. A lot of you got this on the Desmos activity, but it's good to review. What is the general derivative for an exponential function? Yeah, so you're going to write down your exponential function, and then you're going to multiply by a multiplier, which ends up being the natural log of a. Or sometimes it's nicer to write natural log of a first, because then it's a little easier to, I don't know, whichever makes you more comfortable. I think I tend to do the a to the x first, so I'm not getting confused about what the base is. Like, is the natural log part of the base or not? It should be very clear if you write it nicely. Sometimes I just do little things to make it really painfully obvious for me so I don't screw something up. Okay, The exponential shortcut only works on exponential functions. Go. Sorry about that. My nose is wanting to just go crazy today. I guess it's getting close to spring allergy season for me, isn't it? Fun times. Okay, so power functions, we have the power rule. Exponential functions, we have the exponential rule, basically. Okay, so you always want to kind of ask yourself, where's the exponent if you're not super comfortable with that? All right. I think we're ready for the tangent line question, unless there are other concerns or questions. All right, tangent line equations. So the key thing here is line. What's your favorite general equation of a line? Let me know in the chat window. Okay, when I started learning calculus, I agreed with you all. I loved y equals mx plus b. It was like my safe place for lines, right? We're so comfortable dealing with this. This is the slope-intercept form, because you have a slope and you have an intercept. So if you're given the information about a slope and a y-intercept, you plug, chug, and you're good to go. But we're in a calculus class. In a calculus class, we're talking about derivatives. So we have the slope, so that's good. But we're usually talking about the derivative in terms of the slope of a tangent line. So we don't necessarily have the y-intercept. What we end up having is another point. And specifically, that's the point of tangency. So if we're thinking about a tangent line, we might have a graph, we might have some function, we might be thinking about, well, what happens when I have the tangent line here, right? So there's the point of tangency. Point of tangency is where the tangent line touches the function. It's where the function and the tangent line have the same y value, and they have the same slope. So we're usually not being given information about the y-intercepts. We're only given information here. So we have a slope and a point. And so to me, it's much easier to use the point slope form of a line. And there's a couple different versions of this. The one that I tend to use looks like this. You can also do y minus y naught equals m times x minus x naught. And then what I want to point out though is let's update this for calculus. The calculus version, instead of calling the slope m, we might call this f prime. And this isn't all f primes, it's only the f prime at our point of tangency, at x naught. So then we do x minus x naught, and then instead of calling it y naught, we call this f of x naught to reference the fact that this is our function f of x. Okay, so I would strongly encourage you to make friends with the point slope form, just because it's way more natural for calculus. If you love y equals mx plus b, you're welcome to use it. As a lazy person, I just got sick and tired of plugging in my slope, plugging in my y, plugging in my x, solving for b, and then rewriting the line. To me, that was too much work. But if I have the point and the slope, I plug in the slope here, I plug in the point here, and I am done. If you haven't figured this out by now, you'll learn soon. Mathematicians, we're lazy. Okay, so we get tired pretty quickly of doing stuff, so we tend to go for the lazy things. So on that problem, let's see. Now let's pop over there real quick. Okay, so this example from the Desmos activity, write the equation for p prime of x. So we could do this in like shortcut notation. We don't have to use the formal definition for this anymore because this is a power function. So the derivative of negative 2x squared is negative 2 times 2, so it's negative 4x to the 1. And then the derivative of 1,486x is 1,486. Okay, the derivative of 500 is 0. There's no variable attached to it, so that thing, derivative of a constant, is always 0. Okay, so that's the equation for P prime. Now, when you evaluate P prime of 50, we're just plugging in 50. I don't know what that is off the top of my head. I think somebody else had figured it out. Oh, you're just adding 2,000 or subtracting. One thing I've learned, and I kind of hate this about myself, but I am not capable of doing arithmetic while I'm teaching. I will mess it up. It's the same thing, like my spelling is usually pretty good, but if I try to spell a weird word while I'm standing at a whiteboard, I don't know. Spelling goes out the window. Okay, so yeah, 1286. If you have questions while I'm going through this, please let me know in the chat window. Okay, explain the meaning of this number. This would say that at 50, what is the input here? Sofas, at 50 sofas. If IKEA wants to sell one more, like go from 50 to 51, their profit is going to increase by $1,286. Or when they're selling 50 sofas, their profit is approximately changing at a rate of 1,286. Remember that derivatives are telling us about the rate of change. So if you're interpreting a derivative and you're not getting this idea of movement or change, you might want to rethink how you've worded things. Okay, so 3 says, what is the tangent line equation at 50? Okay, so here's my slope, which I need to have for a line. Now I need to have a point. So I already have the input. The input's going to be 50, but I don't know what the output is. That would be P of 50. So I have to compute that. So I need to take -2 times 50 squared plus 1486 times 50 minus 500. So assuming I did the computations right, that should work out. Okay, and so then I need to do exactly this, this piece right here, but I have to just plug in these numbers. So the slope is going to go here and the point goes there. So I end up with, see, this will be the 1286. This will be a 50, and this will be the 68800. So my tangent line equation would be 1,286 times x minus 50 plus 68,800. Okay, and you can totally rewrite that as y equals mx plus b if you like. Or you can be lazy and stop there, unless the directions specify otherwise. So definitely follow the directions, but if they don't specify, and I guess maybe we should spend a few minutes talking about, so like if this graph were p of x, then the tangent line is the equation of this line here. And one cool thing, a couple cool things about the tangent line, at the point of tangency, the function and the derivative have the same y value, and they have the same slope. And if you zoom in, I can't zoom any farther with this program, but like imagine zooming in, there's an interval of, there's like some values where you won't be able to tell the difference between the tangent line and the function. So sometimes the tangent line is linear, the function is usually more complicated. Sometimes we want to use the tangent line instead of the function. So that'll be a topic for next week, tangent line approximation. But if we needed to write the equation of the tangent line, this is how we would do that. Okay, derivatives of combinations of functions. So if we have a power function by itself or an exponential function by itself, or if we're just multiplying by a constant, so like 5x squared instead of x squared, we know how to handle those things now. But what happens if we have two functions that are actually multiplying each other? So like x squared and sine of x, we multiply them, or x squared and e to the x, they're multiplying. On Canvas, there's a bunch of videos. I strongly recommend you watch them because they will pay attention to some common misconceptions, but they also give you better explanations about why these rules exist. So today I'm just giving you the rules, but if you kind of want to know the why or some more examples for implementing, please go watch the videos posted on Canvas for modules week 6, Friday. Okay. There's some really good videos on there to take a look at. So they should be super helpful. All right. So if we have two functions that we're multiplying, unfortunately, we can't just do f prime times g prime. That does not end up working out. And there's some videos that play around with this. So if we have two functions that are being multiplied, we need to use the product rule. And so one thing I might do at the beginning is I might say, well, let's call this function f and we'll call this function g. And then I'll come over here and I'll write off f prime by itself. So what is f prime? Let me know in the chat window. If f is x squared, what is f prime? Okay, awesome. By the power rule, you just say 2x. If g is x cubed plus 3, what is g prime? Let me know in the chat window. Yep, great, 3x squared. Okay, so now the product rule tells me to do f prime g plus f g prime. So I just grab f prime, which is 2x, and then g was x cubed plus 3. And then I grab f, which was x squared, and then I grab g prime, which is 3x squared. Okay, so that would be the derivative of f of x. And if you want, you could simplify that, distribute, expand, whatever you need to do. What questions do you have for me about 1a? Okay, let's just explore this a little bit and make sure we feel okay about that answer. It looks a little complicated. I'm going to actually simplify it for the heck of it here, just to get practice. In general, if you're doing an assessment, unless the directions say otherwise, you might not want to simplify. It makes my life easier for grading. And if you make an algebra mistake, then I have to pay attention to the algebra mistake. I'm doing this while I'm talking, so please, do you agree with me? Did I make a mistake? Let me know how I did there in the chat window. We'll get a chance to check my work in a minute here. Okay, awesome. So we're going to do the same derivative, but we're going to take a different approach. We're going to simplify it first and then take the derivative. So if I multiply that x squared out, my f of x becomes x to the 5th plus. If at any time I'm going too fast, you can just type a W in the chat window, and that'll tell me to wait, or you could say slow down, please, or something. Okay, so if I distribute that x squared, I get x to the 5th.
Sorry.
Yeah.
Isn't it 2x to the 5th?
All I'm doing is multiplying, right?
Yeah, so when you multiply 2x by x to the 3rd, shouldn't, oh, sorry, okay, sorry for that.
You're good, all good. One thing I've noticed as a teacher, and this is totally something I did as a student, is that sometimes in the process of speaking your question, you realize what you were missing. So this is why we do live assessments. This is why we encourage you to go to the Calc Center. This is why I would love to encourage you to speak out in class, because just that process of verbalizing or having to put your thoughts into words can kind of help you realize if you have a question or maybe find something going on there. So that's important. Okay, let me know in the chat window, what is the derivative of f prime from this format? What's the derivative of x to the 5th plus 3x squared? So we multiply by 5, write down the x, make the exponent 1 smaller. Multiply the 3 into 2, write down the x, make the exponent 1 smaller. Okay, awesome. Is that the same thing we got before? So that should help us feel like this weird product rule thing is doing something right. I mean, one example is not a proof, but it should feel a little weird that like, why do you have to do something so complicated? Well, at least it's not completely wrong, okay? Here we have a quotient, so we're dividing. So what we're gonna do is we're gonna pick the top to be F and the bottom to be G, and then we can write out F prime, we can write out G prime. So let me know in the chat window, say F prime equals and put the derivative of F, say G prime equals, put the derivative of G. Let me know that in the chat window. Okay, and then if we put this all together in the quotient rule is F prime G minus F G prime all over G squared. So I do F prime 12x squared minus 6x. I'm going to rearrange the screen here a little bit. Times G minus F times G prime all divided by G squared. So if you memorize the product rule is F prime G plus F G prime. The quotient rule is just keep that order the same, but you flip the sign and then divide by G squared. So be careful about how you memorize this. You want to make sure you get the order on the numerator correct. Okay, and then I'll leave the next step, part B, I'll leave that for you to do on your own time so you can practice, see what happens when you simplify first and then take the derivative. And please do this because I want you to get a sense for, is it better to simplify first and then take the derivative, or is it better to just take the derivative? And there's no easy answer for that. The only way you're going to get an answer for that is if you do 50 to 100 to 150 derivatives and you're like, I hate doing it this way, I'm going to do it the other way. I am not joking when I'm telling you to do 50, 100, 150 derivatives. Being able to compute derivatives is a rote procedure. You can directly control how easy this is for you by how much you practice. So this is one part of the class where simply putting the time in and doing a ton of practice gives you complete control over your grades. Okay, questions aren't typically going to be do this derivative. It's going to be do this derivative, now do this algebra on it, now use it, now interpret it, now talk about this, now do this, now do the tangent line. So if you're struggling with the derivative computation, the rest of the problem is just that much harder. So please, please, please practice the heck out of these, okay? You should do the quotient rule until you are so sick of doing the quotient rule, you will do anything you can to get out of it. And there's a strategy where you can rewrite the function and do something slightly different. We'll learn that next week. And then you should do that strategy so many times that you realize, yeah, the quotient rule wasn't really that bad. I'll just do the quotient rule. When you reach that point, maybe you've done enough practice. Okay, some students like this little ditty up here. So if we think about the top function as the high function because it's on top, and the bottom function as the low function because it's on bottom, we could also learn the quotient rule like this. And so d high would be the derivative of the numerator. Okay, d low would be the derivative of the denominator. So you can learn this as low d high minus high d low draw the line and square below, or all over low, low. It does flip the order of those first two terms, but multiplication is commutative. That's mathematician speak for saying it doesn't matter whether you do 2 times 3 or 3 times 2, you still get 6. But if you like little mnemonic ditties to help you remember things, low D high minus high D low, draw the line and square below, it rhymes. So that can help you make sure you get the order correct so your subtraction is not messing things up. If you're like, that's just weird, cool. Stick with your FG prime. Oh, I actually already wrote this as GF prime. I'm so used to thinking about it as FG prime. I didn't even realize it was written this way on this worksheet differently. F prime G minus F G prime. That's what's stuck in my head. But any way you want to do it is fine. Just got to pay attention and be consistent. So pick something that works for you. What questions do you have? Give me a Y if you're ready to move on. Q if you want to type a question, and I can wait while you get that question typed. If you'd rather use the mic, you can let me know that too. Okay, let's practice more derivatives. So we might call this first function f and the second function g. And so I could write down f prime. Let's see. If your first name starts with a letter in the first half of the alphabet, say through L, put f prime in the chat window. If your first name starts with a letter after L, put g prime in the window. Or put your favorite derivative in the window. I don't care. Just half of you do f and half of you do g, but label it so we know which is which. Okay, so what is f prime? Go ahead and do that computation and type that in. Personally, I would do a little bit of work first. I'm going to rewrite f of x as 3 painfully obvious power functions. So instead of square root of x, I could think of x to the 1/2. And now it's going to be way easier for me to take the derivative. Same thing with g of x. Instead of doing 1 over, okay, so this is 1 over 2x both in denominator. This is the same thing as 1 over 2 times 1 over x. We can split fractions like that, okay? So then I might write this as a negative 1/2 times an x to the negative 1. And then, let's see, minus x cubed. That just sets me up for success when it comes time to take the derivative. If I don't do that, I'll probably make a mistake. So I have to be really careful about those things. Okay, derivative 1 is 0, derivative of the square root is gonna, eventually you'll memorize this, but yeah, for now we could do 1/2 x to the negative 1/2 plus 2x, awesome. And then g is going to give us a positive 1/2 x to the negative 2 minus 3x squared. Love it. Okay, so then putting this all together, I'm going to do f prime g plus f g prime. So f prime and then g was, oh, look at me, I already wrote this out. Plus, and the next piece is f. And the next piece will be g prime. Let's give ourselves, whoops, just a little more room here. Make sure that I have parentheses around everything where I need to have it. keep things nice. What questions do you have on this one? Why in the chat window when you're ready to move on? Okay, same thing. First half of the alphabet, you have F, or you have the numerator. Second half of the alphabet, you have the denominator. Go ahead and let me know F prime, G prime in the chat window. But the G people have it way easier. Okay, so we've got some F prime people here, 3t squared minus natural log of 3 times 3 to the t plus e to the t. Yeah, and what is natural log of e as you're working on this? Think about natural log of e. And this is why that warm-up question on the homework was, what function has or is its own derivative? Okay, so I'm going to pop f prime into place. I'm going to slide g into place. Might need a little extra space here. I can slide f into place. And then g prime, you are telling me, is just what? We have, sorry, let's check in this chat window here. Yeah, G people have the easiest one because pi is a constant, 9 is a constant. Your only variable is the negative t, and this derivative of that is going to be -1. And then you just divide by g squared. So let me know if you have questions in the chat window. Make sure you understand the individual derivatives. Q means you're typing a question. W, you just want me to slow down and wait. Y means you're ready to move on. Okay. So again, you want to do a ton of practice problems to make this, like, this should be as comfortable as breathing and walking. It should be that familiar to you. It'll take a while to get there, but. All right. This is another way of asking these questions that doesn't let you just follow a rote pattern, although it actually kind of does. But this is more of a symbolic version. So let's start by kind of investigating what we've got here. They're defining a function. It's got a quotient in it and a 2. And they're asking us for the derivative of h when x is 0. Should I plug in 0 and then take the derivative, or should I take the derivative and then plug in 0? Does that question make sense to you? Which should it be? Plug in first, plug in 0 and then take the derivative, or take the derivative and then plug in? Yeah, what happens if we were to plug in 0 and then take the derivative? Yeah, we always want to take the derivative first because we have functions that are changing. But if we fix the function and lock it down by plugging in 0, then we're not changing anymore, and so the rate of change would be 0. So we always want to do the derivative first. Cool, so let's do that. What is a formula for h prime of x? So you have to use the quotient rule here. And you're going to be using f, and the derivative of f you could just write as f prime. So let me know in the chat window what the derivative h prime would be. Okay, it is almost just the quotient rule, but we do have a 2 sitting in there, so you gotta be a little careful about that. So we'll have 2 f prime of x g of x minus 2 f of x g prime of x all over g squared. Maybe it would have made more sense just put the 2 out front. That'll save us a computation, right? I'm going to put some giant parentheses around the numerator and just put the 2 out front so I don't have to think that hard. Okay. Cool, cool. All right, so then h prime of 0 is going to be 2 times f prime of 0 times g of 0 minus f of 0 times g prime of 0 all over g of 0 squared. Okay, now I can use the chart. What is f prime of 0 according to that chart? Okay, f prime of 0 is -3. What is g of 0? So I'm still at 0. Oops, when we stop here. So we get 1. F of 0 is also 1. And g prime of 0 is 0.5. We already did g of 0 is 1. So our final answer would be 2 times -3 minus 0.5. Okay. 3.5 doubled, is that 7? I think. This is where my arithmetic brain's kind of like, maybe. Agree, disagree? What questions do you have? Take your time thinking about it, but when you're ready, when you're done, when you're good, throw a Y in the chat window so I know that yes, you're ready to move on. If you have any questions, please stop. There's, half the class is chiming in with Ys, but half the class isn't chiming in at all, so they might have a question. And if you're the brave one to ask, they may be like, oh, thank goodness somebody asked this question. Although you can direct message me. So there is zero fear in asking a question because you can always just send me a direct message. And I promise to do my best to not say, oh, well, somebody just sent me a message and call you out. Okay, let's do part B then. Let's start by writing out, I'm going to move up here. What is the derivative? So we'll start with the derivative in general. So what is p prime of x? Okay, we could just use the quotient rule. And then if we're plugging in 1, we do p prime of 1. So we have f prime of 1, g of 1, plus f of 1, g prime of 1. And then we just go to the chart. And p of 1, so f prime of 1 is 0.5, g of 1 is 5, f of 1 is 3, I think. And let me know if I got any of those wrong, and then you could just simplify that. What questions do you have on this type of problem? How do you feel about it? Variation, we may give you a graph, and you have to read values off the graph. How do you get derivative information from a graph? If I gave you a graph of f of x, how would you get information about f prime of 1, for example? If I didn't give you a chart, if I gave you a picture, if I gave you a graph of f and I wanted to know what is f prime of 1, how could you, it wouldn't necessarily be exact, it might be an estimate, but how can you use the graph to tell me about derivative? Yeah, so you could try to estimate what f prime would look like, but it's easier if you sketch a tangent line on the graph and then try to do a rise over run to pull the slope information off the tangent line. So if you have a graph of f and you need to know about f prime, I would sketch a tangent line and then do that rise over run triangle to try to get the slope off. Awesome. Okay. Sine and cosine are graphed below. Let's take a look at their derivatives. So if we're going to sketch a derivative, I like to start by asking where the slope is 0. Where's the tangent line 0? So I'm going to draw all these little horizontal tangent lines, and that tells me the places where my derivative graph is going to have to cross the x-axis. So I'm going to graph the derivative in red here. Okay, and then in between, I don't know what that is. It's probably going to be a multiple of pi. In between these two values, I notice that sine is decreasing. So f prime needs to be what? Well, so if the function is decreasing, the derivative is either positive or negative. Which is it? Yeah, f prime is negative. So it means I need to be below the x-axis. Where do I have the steepest tangent line? Because I start off at 0, right? These tangent slopes are 0, but then they get steeper. And where does it look like they have the steepest? I think the steepest tangent line is actually when x is equal to, when y is equal to 0. And so that means that that's where I have to have my maximum steepness. Now, if I actually try to like sketch, I don't know if I picked good points here, but what do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9 boxes. I don't think I picked very good points. Let me clean this up just a little bit. What is the approximate slope right there? What do you think the slope is? Are all these boxes the same? These boxes are not going to be the same. Okay, so that's each horizontal box is a 0.1. So that's a 0.5 units up. And then each horizontal box is also 0.1, right? Sorry about that. So that's 0.5. So we have 0.5 over 0.5, but it's a negative slope. So the negative slope is equal to, actually looks like it's going to be a -1 there. Yeah. So we know that we need to be maximum slope all the way down here. So the graph is going to look like this. And using symmetry, we can kind of cheat and just say, oh, it's going to be the same thing, reaching a maximum slope of 1 or -1, passing through those zeros. Got a little tight there. Okay, so the graph kind of tracks like that. Any guesses on what that graph is of? Yeah, that looks like cosine of x, cosine of theta in this case. Okay. So there are proofs of this on the book, there's proofs online, but from here on out, let's just say that if we know the function is sine, then we can just say the derivative is cosine. Okay. We will do more trig stuff next week. So this is on the webwork, I think. It's really good if you can learn this one. So go ahead and memorize that one. The rest can follow. If you need to go, it's 2:50. Feel free to leave and have a great weekend. If you want to stick around, we'll do the derivative of cosine. If you have questions, let me know. But it is 2:50, so feel free to leave this Zoom session and enjoy your weekend, or if you have other classes. The homework did get graded, by the way. Oh, yeah, that's a good point. What should we do for participation? Chat box? If I don't see you chatting, then I will look at the Desmos activity from yesterday. So yeah, so the web work, I suggest you do problems 1 through 4 tonight, just because I want you to get in the habit of not putting off the homework. I was talking with another student about scheduling, and he was like, yeah, I learned I need to start these assignments on the weekend. I'm like, yes, you do. You cannot put everything off to the last minute. So I would recommend you spend some time doing some web work. There's not an actual due date, but you should make it a personal due date. Like, I commit to starting the web work, to seeing how long it is, to seeing how bad it is. You can do the derivative ones at the end now. You have enough for that. And there's some tricky ones that make you think. So I would suggest not putting it off. So yeah, if you want participation points, give me something somewhat significant in the chat window. Otherwise, I will kind of give you the benefit of the doubt and take a look at the Desmos activity. What is closed, Nasser? Is that the web work? Huh.
Yeah, I want in Canvas, there is no link for the web work.
Okay, so the web work link, you can always, it's the same website no matter what. So even if I didn't post web work 7 in week 7, go to the week 6 one and you'll get there.
Okay.
Okay, I will try to publish those. I apologize for that, but you can always get to the web work assignments through the web work website. You can possibly even Google CSU Math 160 web work. I don't know if that works, but yeah, the web work is a separate entity from Canvas. So participation. Pardon?
Yeah, I was going to ask about the participation. I didn't hear you.
Participation for today, use the chat window to let me ask something fairly significant. Otherwise, if I don't see your names in the chat window, I'll go look at the Desmos activity from yesterday. But I'd prefer to just run through the chat window today, since that was actually class. So if you're still on and you haven't said anything in the chat window yet, let me know what you think y prime is if y is cosine. What is the derivative of cosine? Yeah, and if you need to leave, feel free. Thank you for your attending and your participation in the chat response. Yeah, so it's not straight sine, right? Because sine goes through the origin with an increase. Sine's right here. There we go. Sine is over here, right? We increase to the origin, but this graph is actually decreasing through the origin. So this one is actually the flip. I should have done that in another color. Sine of x would be right here. Something like that. So yeah, this is flipped, and we do flips by multiplying by -1. So negative sine of theta. Cool. What other questions do you have for me? It'd be fun if you tried tangent by thinking about it as sine over cosine. But I would say you don't need to worry about the rest of the trig derivatives until next week. We have time for those in the schedule for next week.